Hello, I attended a Silicon Valley AI, machine learning, and computer vision meetup. The event was through Zoom and hosted by Brent Griffin. Brent Griffin gave a very insightful presentation on his work with visual AI, computer vision, and robotics. Brent Griffin is a principal research scientist at Voxel 51. Voxel 51 works on improving the future of AI and computer vision with its open source platform 51. They specialize in low-cost machine learning and unstructured data at scale. Visual AI is a subset of AI that processes visual data to provide humans, physical systems, or software with necessary insights for informed decision-making and action. Brent's work with computer vision and video object segmentation showed the data was useful for human insight and information, but was not designed to be used for a physical robot application. On the other end of the spectrum, working with two-leg bipedal locomotion purely focused on control of the robot's movement with little to no external sensing of the robot. The robot could only perform in structured, controlled environments and required the use of fiducial markers to help guide its task. Many robotics companies are more focused on improving hardware rather than implementing their own software because they believe that a computer vision professional can come in, provide the signaling software, and things will work coherently. Unfortunately, that is not the case. Brent's goal became to design visual AI and robotics that can work cohesively using reasonable signals from computer vision that will not require prior 3D scans of the objects. This requires less data along with the same efficiency and reliability of the system. Visual servo control and vision-based manipulation are ways that visual AI can serve robotics, but also a way for robotics to help computer vision improve through depth from motion and detection and self-supervised depth estimation. Depth from motion and detection is where odometry information from a physical system is provided to a visual AI system and can infer 3D information about the environment that is going to help the robotic system work effectively. Self-supervised depth estimation is the robot's ability to continuously collect data and refine its abilities for depth perception. Visual AI is highly dependent on massive amounts of data. Take ResNet for example, which was trained using an estimated 1.28 million images. More recent models such as CLIP run on 400 million images, which is a significant leap in data collection and analyzation. The increased requirement of data for visual AI can actually be solved through the use of robotics, where imagery can be collected in a few hours. For example, visual AI models are trained with robots in the specific environment where they will be working. If the model generates data relevant to the task that is performing, and it does so at a massive scale. If changes are happening in the environment, it can capture that as well, essentially designing a robot system that is collecting its own data and using that to improve its own visual AI system that in turn helps the performance of the robot. Brent was able to apply these goals with his work done with Toyota Research Institute, which hosted a tournament for teams to receive a grant, a human support robot, and an invitation to compete in TRI's HSR challenge of the improvement of their HSR. HSR was developed to help the disabled and the aging population in Japan. However, the robot was lacking versatility. HSRs had difficulty finding and manipulating objects in unstructured human environments. Currently, HSR only works with controlled structured environments and relies on fiducial markers to perform identification of objects correctly. TRI's HSR challenge was created to gather people who strive for the advancement of robotics and AI software to create visual AI that can allow the HSR to detect items and place them in specified locations in the desired position. Brent's team ultimately decided to use an RGBD-based object recognition using the two cameras on the robot, one on the head and one in the hand of the robot. RGB segmentation identifies the object while the depth allows the robot to gauge how far it needs to reach for the object. Classical visual servo control was used for this application. This allowed the use of visual data as input to a servo feedback control loop. The data collection occurred using classical and deep learning based video object segmentation, which allowed for the operation of unstructured human environments. The learning control module also used Hadamard-Broyden updates. These processes allowed the robot to detect the item and position itself close enough to reach for it. Using the hand camera, a segmentation mask of the object in 3D space was placed into a plan along with a segmentation of the grasper. Using the two masks, an equation was used to find the thinnest overlap of the two masks so the hand can rotate into a position to easily grasp the object. The general overview of the challenge was to help TRI gather data and implementations to understand how computer vision, visual AI, and robotics could see and manipulate an object using multiple factors such as item type, color, shape, and deformability. Challenge, the teams had to generate a working visual AI for the robot to be able to identify colored blocks and place them in appropriate cubicles. The second challenge introduced a banana, and the goal was to identify the banana and place it separately from the blocks. The third challenge introduced more random objects so that the robot had to identify more between blocks and objects, and voice commands were used to guide tasks. Using these challenges, Brent's team was able to see how visual controllers automatically learn the relationship between visual features and actuation and create a policy for it. This meant that the robot had different options for what mode it would be in. This was used in the fourth challenge, where they were able to use segmentation of an object as a resource to complete the task. Using these voice commands, the user will request the robot to pick up an item. If it had trouble locating the item, it would eventually apply the help policy, where it would request help from the user to locate the object's location by walking over to it. The robot could track the user's movement and make its way over to the required object and pick it up. The last challenge was also very interesting to witness, as the robot was requested to analyze random objects, decide if they were deformable or not, and organize them by placing them in a container with a 2x2 inch cross-sectional opening. If the robot decided the item would not fit in the 2x2 entry point, it would place them in a second bin that would need human reliance to investigate. The changes on the object segmentation was used for the robot to make the judgment if the object was deformable or not. The use of this learned data eventually led to the ability to train the robot to take a few images of a ball and then track it when pushed around. It also allowed for the placement of cups into their color-coordinated bins that were swapped each time a cup was placed. Depth perception was analyzed using depth from motion and detection. The size changes of the object from multiple different distances perpendicular to the object allowed for changes in optical expansion as the camera moved closer to the object. Moving the object laterally, seeing the distance change from optical expansion, motion parallax was used to determine the estimated depth of the object has changed in comparison to the camera. This allowed the robot to analyze this distance and predict how far to reach his arm in order to pick up the object. Will become very useful as they are to be implemented in the Toyota Woven City, a new built city that is designed for humans and robots to live synergistically. This would push for the construction of buildings to have both humans and robots live in environments so that many tasks can be done robotically. I briefly was able to chat with Brent about what the biggest challenges was working with TRI, and his response was, "I found it most difficult getting the robot to recognize reflective objects that were placed in the cubby and have it be efficient. The robot was required to move a precise movement in order to gauge how much its camera was moved and take images also at varying angles. Due to low range of degree, it was difficult for it to analyze as quickly as it did with objects on the floor. I hope to work further on the project at Woven City as something I'm incredibly interested in." My final thoughts, I enjoyed the presentation and the challenge that was presented by TRI. It seems that they were able to really captivate a lot of research from the brilliant minds that participated and inspired me to join future events or competitions. I learned the different processes that computer vision is used and how visual AI can be used to improve a robot's capabilities. Self-driving cars such as Tesla rely similarly on these methods. Intro to Machine Learning featuring computer vision was my campus meetup. This meeting was to give students an introduction on how machine learning and computer vision work together. It allowed a hands-on on both of these applications to set up provided code to identify flowers from different data sets. In the meeting, a slideshow was presented to talk about related terminology of machine learning, such as deep learning, convolutional neural network, intuition, train data, local filter, convolutional layer, and max pooling. Using Python and Google Colab notebooks, a guided tutorial was given to us to help us understand the basics of machine learning. We were tasked to upload data, have the program execute, and then adjust data to see how things change. Machine workflow examine and understand data, build input pipeline, train the model, test the model, improve the model, and repeat the process. Stack Overflow question, I was using a project that required Java, and it's a programming language that I'm not familiar with. I needed help getting user input to validate a 4-letter alphabetical input. Luckily, a community member responded with a great answer to the question. He gave 2 options, where one was used for speed and the other for readability.